Okay, we should start. So let's quickly review what we have done on Monday. I hope you have a nice break yesterday. So random variable, as probably you might have recalled, is a way to assign numbers to outcome. The reason that we need to assign number to outcomes is because of the we often record numbers to represent outcomes, and in making numbers to outcomes, that we make our life easier. And very often we actually care about the numbers instead of the outcome itself. Okay, so this is the way that make our life easier. And then what are the numbers you can put in? It's called the support, or the random variable, the support. And based on the support, we can distinguish they are discrete or continuous. And discrete, that means that usually we talk about integers, right? And for continuous, we talk about real numbers, right? It's just like decimals. So that is how usually you can think in your mind. Of course, the technical definition is more involved, but I think it's okay. You can think discrete is just natural numbers, and continuous are any positive numbers. I mean, negative also fine, but I mean, usually we deal with positive numbers in most cases, but that's also fine. And then because of we have a number that makes some way we can work on it is what we call the probability functions and cumulative probability functions. What are they? And they're the way to describe the random variable, right? The easiest way to think is look at this graph, right? The left-hand side is px, the right-hand side is fx, right? And px give you what is the x, I give you what's the p, right? So give me the value of x, I give you the probability p equal to x, right? The x is the value, right? And then the fx will be the probability that equal to or less than that value, okay? And you may ask why we care about the big F instead of P. It's very natural for you to think discrete is the way that you use when talk about discrete, okay? F with the way we will use it for continuous, okay? But there is no difference for our purpose that they are the same, okay? Just like looking at the different, same coin of the different side, right? You can jump between P and F, right? You have your P, you can go to F, your F, you go to P. So you should be able to figure out between P and F by yourself. If I give you P, you can tell me the F. I give you F, you give me P. Okay, so that would be the case. And because of now we have the sample space of numbers, right? That's why we can use the idea we learned in the topic 1, right? Topic 1 said if we're numbers, we're able to summarize things from talking about mean, variance, kurtosis, and skewness. And why we have numbers? Because it reverses the idea we have probability, right? Because probability imply from the classical definition is if you repeat the experiment many times, right, the probability ratios or the relative frequency, right, of that event occurs, right? Just like if you have a coin, what's the probability of tail is you repeat the experiment many times, right? It's number of tails over number of tosses you have done. Same here if you have a if I give you a random variable, right, and a discrete version, right, and then you give me the big P, right, is the probability, right, for each value of x, and then you imagine yourself just repeating this experiment many times, right? Then the relative frequency, the number of the times appears, will actually given by the probability, right? So the expectation is actually just you repeat this experiment many times in your mind, okay? And you get a data, you actually calculate the mean, is exactly the expectation. So expectation is actually mean. If you repeat this experiment in your mind, okay, keep doing that, and you calculate the mean, right? Just example would be you have the mean, right, of head when toes correspond once, and you repeat. If your head you have 1, you have tail you have 0, then repeat many times, right? The mean is basically just 1/2, right? Because it's half of time you have 0, half time 1. Average of these numbers would be 1/2. Same when you have the die, right? If you just record the numbers of the face that you face upward, right? It's up 1 to 6, right? And then you repeat 6 million times. You should expect 1 appear 1 million times, 2 appear 1 million times, and so on and so forth. Each number appear 1 million times. So that's why the average of these values it give you 3.5. Okay, I hope that is clear. What's going on here? What's the mean? You just repeat the experiment. You just calculate actually the mean. Okay, and we also mentioned there a nice probability expectation, which you can separate calculation, right? If there's a linear operation, you just multiply and add, then you just basically can separate the operations, can just calculate the expectation and just multiply and add later. Okay. Do note that just to remind you that this only works for expectation. For variance, then they will be different. Okay. And when variance is same as what we have in the topic 1, right? If you repeat this experiment many times, you calculate the mean and you subtract its outcome from the mean and take the square and times probability, right? But it's the same as you repeat many times. You have many data there. You just calculate the variance as we do in topic 1. That's the variance, and the interpretation is the same, just like how the data are deviate from mean, right? If your observation is likely to deviate from mean, then the higher variance, right? It's a spread. The same thing. You can imagine you can calculate kurtosis and skewness in this context. There's certainly no problem doing that. Okay, and the reason we don't mention it because it's you can do it, but that would not be required later. As you receive it, because we focus on bell curve in normal distribution, and in that case, the skewness is always 0, the kurtosis is always 3, and you may ask, what if the random variable we care is not normal? And that, of course, will be reserved for more advanced class, right? Then in that case, you would be deeply worried about those things, and that would be a concern, especially about finance, right? If you try to look at the development of finance theory, it's like in the old day they're okay with the bell curve, but increasingly they are not very happy because it's not really a good thing. I mean, same as actuarial science, they look at the things and they figure out that it's not normal is not a good way. I mean, there will be a much easier way, a much more better way to do it. But for our class, I think normal is fine, and that is coming from the idea that we learn in this class. We call the central limit theorem. Later, in topic 5, that said, if you have large enough number of data and some other conditions are met, then we should expect a bell curve comes out. And bell curve actually comes out a lot of cases like IQ, your height, your weight, and look at the public exam scores and so on and so forth, right? And of course, when the sample size is small, then probably the bell curve doesn't work. But in a lot of cases, it will work. I mean, if it doesn't work, you collect more data, it works out. So for business application, usually it's not a big concern these days because of what we call big data, right? You have actually more data than you need, or the data has a huge dimension, then you really don't have to worry those. But at the moment, I mean, that I think it's okay for just let you know, we're focusing on normal distribution, so everything would work nicely. So the variance that the calculation is simple, just like you subtract each outcome by its expectation, take the square times probability, and so on and so forth, and you get the variance. Okay. And this formula, the first formula is, I recommend you to know it. It's not memorizing, but it's just saying that if you see, you're not going to be surprised because it is in the proof, every in the proof. But although we don't talk about proof in this class, but you should not be surprised to see it because it's just a mathematical result. It's another way to interpret variance. It's not very important, But if you want to do calculation by hand or by computer, there's another way to do it. And so usually this is the easy, faster way to compute it. But the important thing lies on the second and the third formulas. The second one is saying that if you have a B, a constant, you add to the data, so add the random variable doesn't have any impact. Okay, the interpretation is looking at the variance of your portfolio. Whether you have more cash or no cash actually doesn't affect the variance. The cash is not going to change. So adding B or subtracting from B from your portfolio actually has no difference because there's no uncertainty there. Right? That part doesn't affect the spread of data. You just move the data points moving around, right? Just like the data point on a data line, and you just shift everything to the and the side has no worry about the variance. And do note that the variance, if you multiply by constant, the variance will increase by a squared. Okay, so that actually is a little bit counterintuitive, but if you think about the standard deviation, right? You multiply by a times, then the standard deviation should also increase by a times, right? So that means the variance must be a squared. So I hope that is easier way to remember it because of the standard deviation should grow as the original data, then the variance must be growing by the square, right? So I hope that is okay. The last one is a little bit non-trivial, but we focus on a special case where they're independent. Okay, if the variance of the sum, if these sum are independent, then it's just sum of the variance. Okay, so we can. This is very similar to what we have in expectation, right? Expectation of the sum is sum of the expectation, right? And this said you just can separate them out, right? If they're independent, you can just focus on calculating the variance of one guy and the guy to add up together is fine. Okay, just like this said, if they're independent, right? You can evaluate that risk independently, right? Suppose you invest in US or invest in the Earth or invest in the Mars, right? A different planet, then you expect the risk may be different, right? So you can completely separate them, or invest in the US stock market or invest in the cryptocurrency, probably you might think the risk is more like independent. So you can when you try to look at the risk with the US stock market and cryptocurrency, maybe you can separate them, right? But in the most cases, they are not independent, right? In that case, you have a complicated formula, as we have said here. You have to take care about the covariance, right? And we learn covariance in topic 1, but we don't talk about this because it requires you to learn what we call multivariate random variable. You need to learn much more involved concept, which is beyond the scope of this class. So we focus only on single variable random variable. Just mean that when you have a outcome from the random experiment, we only use one number to represent the outcome instead of 2 numbers or 3 numbers, right? If you allow ourselves to represent the outcome of random experiment using 2 numbers, x and y, then we can talk about these things, okay? But for our purpose, we only restrict to only 1, okay? The reason is not being we are lazy or what, but the mathematical tools require is much more involved that beyond the scope of introductory class. I mean, you look at any introductory statistics, they only focus on single variable. Okay, so even you go to stat department, I think they don't talk about that, at least for the introductory class. Okay, but that being said, I mean, that is a huge topic, and if you are wanting to go further, you should know it. And especially for those who are doing quantitative finance, they should check carefully what's going on there. I mean, the idea is very similar, but the math is more involved. So that's I guess it's you will learn about it when you actually face it in the future. So just let you know there's something more involved there. Okay, and actually you will, even if you don't know the background, you can actually apply it, right? Just the stock right here with example of investment 2 stock, and we assume the independent. That makes our variance calculation easier, right? But in terms of expectation, you don't have to assume for independence. And here we saw with the independent, there's a reason why you want to mix the two stock, right? We want to diversify. The reason is being that the mean, the expectation of the portfolio return is actually mixing how you mix the linear combination of X and Y, the mean return, right? Just like if you half invest in X, half invest in Y, your return is just half of the return of X and half return of Y, right? But the variance is much lower, right? It's not halfway between 0.01 and 0.05, right? So it does mean that diversification is good. And in this particular case, why is good? Because the independent, right? When the independent is good to diversify. And that explains why we see in the investment world, right? We always try to look at things that are independent of what is been available, right? That's why we have a hedge fund, we have startup, we have cryptocurrency, we have gold, right? We have collectibles, we have antiques, we have beers, we have wine, we have watches, right? Those are more likely independent of the aggregate stock market, right? So that's why these things are valuable, right? And in some sense, right, that's why you study, right? In some sense, studying is getting you human capital, which is unlikely related to what happened for the business cycle, right? So you keep accumulating your human capital, keep learning in school, right? It's usually good investment because usually independent of the risk that you're seeing. Of course, your earning eventually may jump up and down with the whole economy, but that is less correlated than other things that you're seeing, right? And so that's why a lot of people would like to work in the civil servants, right? Work for the government, no matter Hong Kong or China or everywhere in the world, right? Because work in the government or some big corporation actually make the variance very low, right? Because usually you get employed for sure, right? So that. So we will talk about after this. We talk about some common discrete distribution, and you may ask why we do that. But these are the things that usually that arise from application that this thing would naturally comes out. And of course, you will ask, as I said, right? Are they going to the bell curve? Yes, they will if you have a very large sample. Okay? If large enough, then actually you can use bell curve. That's no problem. But what happened is bell curve doesn't apply, then you better use this, and that actually fit things better. I guess I covered the uniform. Uniform actually we have been doing a lot of time, like just rolling a die, right? It's 1 up to 6, and each outcome is equally likely. Okay, tossing a coin once is yes, right? If tossing a coin twice is not, okay, because not every outcome is equally likely. Okay, unless you are willing to assign different numbers from what we have been doing, because this one we have been assigning, this is right, it's not same for each outcome, right? Unless you assign this is 1, 2, 3, 4, right? Only you're willing to do that, then it's uniform. But in this case, it's not uniform. Okay, just then you know. Of course, later you will see this is just a binomial, but that one is not uniform. Okay, just to make sure that you know. Although I say tossing a coin, but just toss once. Right? If more than once, you have to look at the binomial we will talk about immediately now. Okay. So uniform distribution, and this looks trivial, but actually sometimes arise a lot of time if you see things more carefully, because this is the easiest way to handle things, right? Even if there's some different from the equal for each one, then maybe your data shows up like similar to equal, then the uniform might be a good approximation. Okay, and I think last class we finished with a binomial distribution, right? And here is the sample space can be very complicated, okay? But what we are using is a very crude way or two-way to summarize the outcome. It's just like failure success, right? It's whether there's a 1 or 2, right? It's like toss and coin. We just say these are success, these are failure, right? That's the dichotomous classification, right? Is very often we do, right? Just like the exam, we have a pass or not pass, right? So it's not something natural, right? And here we have probability of success P and failure is 1 minus P. And if there's 1/2, it's a toss and a fair coin, okay? And the variable is number of success, okay? That's either 0 or 1 because only toss a coin once, or just conduct this experiment once. And you can write the probability function as like this coming from the following table, right? 0 is 1 minus P and 1 is P, okay? And this is the simplest way you can think, right? And as I said last time, this is the way you can summarize the table, right? Because when x equal to 0, okay, the first term, this px is 0, right? This is 1 minus p, right? Because 1 minus 0 is 1, right? When x is 1, this term is just p, the last term is just 1, okay? Because 1 minus 1 is 0, raised to the power 0 give you 1, okay? So that is this function, right? And we explain why this expected is p, right? I mean, this is directly follow from what we're expecting when we toss a coin, right? So it's because of you repeat many times, right? Suppose then you have p times of success, right? If you have say 100 of times, right? Then you have 100 times p number of success, right? And the variance is p times 1 minus p. Just to remind you, we have why with this is when p is 0, right? Then everything is a failure, right? The variance is 0. When p is 1, then everything is success. There's no variance, right? The highest variance only occur when p is intermediate, right? Actually exactly 1/2, right? When p is 1/2, that's the maximum variance. Okay, I hope that's clear because we will talk about binomial based on this one. Okay, so this is the graph, right? And we'll talk about binomial, and I will say binomial is the one of the most useful thing when talk about discrete random variable, and because a lot of things are based on this one. Okay, and binomial distribution is basically you're repeating the binomial trial n times. Okay, just saying that it's similar to just like toss a coin n times. And independent means that each trial is independent. Okay, so that's the toss a coin, right? The first time you get a tail doesn't help you to predict the next one, right? So just remember what you learned in the last topic, independent, right? Means that conditional on what happened in the first trial doesn't help you to say anything on second, right? Or conditional on the second trial doesn't help you anything about the first one, right? Or the probability of having 2 success, right? It just probability success on the first trial times the second one, right? Just in case you don't recall, let me write down here because I guess that would be, just say if A and B are independent, right? This is what we have, right? A given B, it's just A, right? You know, also you can reverse this, right? B given A, it's just probability of B, right? And also for the B and A or A and B, it just multiply, right? So this is definition, and 3 of them the same, right? So basically, just like independent means we can look at things independently, right? Without regarding what happened. Each one has no relation with the other one, right? And each one is identical, right? So each trial have probability success of P, okay? So just like tossing a coin many times, as we have been doing many, we have implicitly implied already, right? Tossing coin 2 times is actually, we are saying independent already, right? So that is already in our terminology. And next is the number of success, right? You have n trials, right? So you can either have no success or 1 up to n. So the n plus 1 possible outcomes, okay? It's not just n plus 1 because you can have 0 success. Okay, so that's the support will be coming from 0 up to n. Okay. And actually, using combinatorics, we know the probability like this. And this actually coming from the example of we have at the end of the topic 2. Okay. But let me explain why this is true. Okay. So here, look at the blue one first. Okay. Look at blue one first. What's the meaning of this particular expression? Okay. This exactly means if I have X success, right? So each success has probability P, right? And let's consider the following sequence of event would happen. We have n trial, okay? Let's consider the first X are successful, but the rest are failure, okay? We success for X time, and fail for the rest, okay? What's the probability of doing it, okay? And the probability of this is an intercept, and right? So let me write that down. So you want probability of, let's call success is success, right? First success, second success, up to X success, right? And we have failure of X plus 1, up to F of n, right? So this is what we want to find, right? We have first success, second success, up to n success, X of success, and X plus 1 is failure up to the nth one are the failures, right? Remember the idea what we have here is independence, right? Independence is actually you don't need to care what's going on, right? The order. So you can just separate what's probability of S1, probability of S2, right? Just multiply, right? Sx and failure of n plus 1 and failure of n, right? And you do know that each one are the same. You just p, right? For this one, p, and these are 1 minus p, 1 minus p, right? So that actually you have x of p, so that's why you have p of x here, right? So coming from this guy, right? And you have this coming from this one, right? So there are x of p and n minus x of 1 minus p, right? So that's how you get this blue one, okay? Is that clear how you get the blue one? First of X success and the rest are failure, okay? Is that clear what's going on? Now, this is not done yet because we just focus on particular sequence of event, right? Just like focus on success, 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 and failure, failure, right? But we can have first failure, right? We can have something like this, right? We can have alternative. You can think, say, I don't have first success, I have failure first, but I have success, okay? I have X and up to X plus 1, but again, I have failure of X plus 2, okay? And so on and so forth, right? So I just swap the 1 and the X plus 1, right? The same. And the probability the same, right? Because when I calculate, it doesn't regard with regard to the order because they're independent. The same probability will happen, okay? So how many, because we're X equal to X, right? So how many of these we can make, right? It's exactly NCX, right? Why NCX? You just imagine in your mind, you have n balls, right? And each ball have a number there, right? Number 1 means if I draw a ball number 1, I have first success. I've drawn ball number 2, I have 2 success, right? Now I have n balls, I want to draw x balls because I just want x success, right? So that's NCX. Is that clear? I think we have exactly the same example when we have our top end of the topic 2. If you can't recall, in case you don't, let me go back to have the topic 2 here. Okay. So if you still recall that example is this one. Not this one, sorry. It's this one, right? You have a total coin 4 times, right? That's why how many of them is exactly 4C2, right? So exactly the same happening goes on. Okay. Is that okay why this is the case? Of course, if you don't appreciate that explanation, doesn't really matter, because at the end, you just memorize this formula for the moment, and slowly you appreciate after a while. I mean, it took me quite a while to understand what's going on there, but I don't expect you immediately fully understand why the formula works. But if you really try to work out, try to draw a tree, okay, n equal to 2, equal to 3, and so on and so forth, hopefully you're convinced what I'm saying. Okay. Is there any question? Because I do see this is not an easy one. Is that okay? If no, then let me erase. This for record. Okay. I think I explained why this is true. Okay. So I think the main thing you would see is the mean and variance, okay, which is NP N1 NP times N1 minus P. Okay. You can prove it, but let's do it in an easier way. The thing we learn, right? So we learn the following. Okay. Actually, a binomial random variable, suppose you have 2 outcome, right? You can write as just sum of the 2 binomial random variable. Suppose X is a binomial. It's a binomial. Okay. You can write this as Bernoulli. Okay. Because you just because you just consider each one is binomial, add them together, right? Then you have n of them. Okay. So that's why the mean of the binomial is just sum of the n mean of Bernoulli, right? And each mean of Bernoulli is just p. So that's why we have n times p, right? Because remember, the mean of the sum, right, is sum of the means. We just mentioned about the linear property of expectation. Okay, because this is coming from the fact that we have said expected x plus y is just expected x plus expected y. Just application directly here. Okay, of course, if you want, you can prove it directly. That is what in the technical slide included. You can just check it out. That's a direct proof for that. But if you don't like the proof, actually we don't have to, because this is a direct goes to that one. And the next one, the same idea here, because each are independent, right? So that's why variance of x plus y is just variance x plus variance y. All right. Do note that this comes from the fact that x and y are independent. Okay, this is only true for x and y independent. And we're talking about binomial, which is each trial is independent. So that's why this formula actually directly apply. Maybe I have a bracket here to make sure that it's clear what's going on. It's calculated. Okay. And again, you would expect the same thing would happen, right? Just like if the P is very big and very small, you don't have variance, that was expected, right? The same thing would apply. Is that clear? Is that clear what's going on? Okay. And I hope now I will try to convince you this binomial is a useful case by giving you application. Okay. And as I said, this is very useful because it applies to many things as long as you are able to distinguish, you're going to summarize things by just 2 possible outcomes, right? Either success or failure. Okay. If you can do that, then binomial would fit very well. Okay. And let me go to show you the example. Okay. This example is very useful if you are a small owner of business that operates, say, buffet, or you are preparing food which require unfrozen from the fridge, right? So you have a 30% of customer like spicy food, and spicy food probably you need some preparation, right? You have to marinate it before you can do it. The problem is you don't want to over prepare the food or under prepare. So how can you do it? You just look at the data, okay? 30% of customer like spicy food. So now the question is, we have 5 customers coming in the next hour or so. So you are figuring out, okay, you don't know what they're ordering. So how much food you're going to prepare? One way to calculate, say, what is the probability, right? Look at the probability is like 2 people like it, right? And it's just simply this question is just like assuming each customer is independent, right? With n equal to 5, right? And we have p equal to 0.3, okay? And x we're asking just 2, okay? So basically is n, right? This is x, right? This is p, this is x, this 1 minus p, this is n minus x, right? So just put all the number there, it give you 30%, okay? So 30% of people with 2, right? And then you can calculate any probability, right? Given this formula. And then you can, if with this probability, right? Although we don't put it here, but you can have a model to tell you how much food you should prepare, right? Given the probability, you can have a decision to decide based on cost and benefit, right? Of under prepare or over prepare. You can have a loss function. You can calculate what is the optimal way to do, okay? But I think we are just not talk about this further, but I think this is already enough. You all know the probability, you know the consequences, then you can figure out some way to best plan your food, right? And you can see this is pretty much applied to a lot of business application, right? Because look at the consumers, look at things happen. Maybe you're looking about, say you are the subway company, right? And then you figure out that, 5% or some percentage there, some train may go defective or not working as planned. Then you have to figure out how many reserve capacity you want, right? Or you are the human resources manager, then you figure out that some percentage of staff may get sick, right? Then you have to figure out how many part-time worker is hired to make sure that everything is going smooth as normal days. So there are many things you can apply, as long as you can divide them into success or failure, right? Which often the case, right? But probably you will ask the question, what if we have more than 2 outcomes that we need, right? We want to have not success or failure. We want more than 2 outcomes. And indeed, they're what we call the multinomial distribution. The math and calculation are very similar, okay? But we don't talk about them here. You can check if you want and check your Google, check the multinomial, just your binomial, just swing to multinomial, everything will look very similar. Of course, things will be a little bit different, but that can be done, can be generalized, but we just focus on the simple one. And this is already have a lot of application. Is that okay? Is there any question about the binomial? Okay. If no, before break, I want to talk about a related question as well. So here it's just like we just focus on 2. What happens if you ask no more than 2 spicy food? In that case, right, without going to the answer, we just looking at the calculator, look at the answer first, right? See here we have 83% and no more than 2. Okay, we'll go to the calculation later. And you can see that if you're the restaurant owner, probably you don't need to prepare more than 2, right? Because a huge, very unlikely that, only for 17% that you have more than 2, right? So basically you just need to prepare at most 3, right? Or even 2 of the food that would be sufficient, right? The calculation is very straightforward, right? Basically just adding 0, 1 up to 3, right? Then give you the answer. Of course, you will see the calculation is rather tedious, right? You have to calculate combination 3 times. But of course, later you see when talk about Excel, then just one key and you're done. Okay, just one formula, then you are there. Okay, but you know what is behind. I mean, the calculation is very quick in terms of Excel. Okay, but if you do it in your calculator, you need some time to do it. And of course, you know Python out, that will be even faster. Okay, is that clear what's going on? Okay. Is there any question about binomial? I mean, you can see the binomial is, I think the application has a lot. I mean, we don't have time to cover every single application. If you want to look at the textbook, look at the online, you will see a lot of applications for binomial. So it's not, it's a very widely used one. Okay. And I don't go to the proof. Okay. But before we break, I want to talk about Poisson a little bit, introduction. And the Poisson, in fact, if you look at from mathematics, it is exactly a binomial, a special case. What do I mean by that? It's exactly talking about, as I show it here, it will be when n is very large and p is very small. Okay, just consider a binomial. You have very big n and p is very small. Okay, so you may ask, what is the application of this, right? Why we care about binomial when n is very big and p is very small? Okay, it is just a good way to model how many things are happening in a period of time. Okay, just to give you the idea. Okay, binomial is the following, right? Say suppose you have a box 1, box 2, box 3, so on and so forth. We have box n, right? Each outcome is either success or failure, and your p and 1 minus p, right? Probability, so and so, right? And there are many. There's a discrete number of cases, number of outcome, right? Number of customer there, right? So constant number. Okay, just talk. There's no time dimension here. Okay, now we just consider another related case is we consider n is very large, so we just keep go on, just like 1 up to many. This is very big. Okay, very big. And the event success will probably p when this is very small. Okay, so this actually corresponds to the idea that you consider is you have a time horizon, okay, from 0 up to t. Okay, and n is very big means that I cut the time interval into very small interval, right? Sub-interval, very small interval. Maybe t is an hour. Okay, and you cut each interval is 1 second. Okay, and what's probability that would happen here is, say, maybe you are the restaurant, you're saying with probability p, very small probability, someone will enter the store, right? And in this context, we're considering that at that 1 second, there is either one guy come in or no guy come in, right? There cannot be 2 guys come in 1 single second. Okay, or if you think it's still possible, you can just divide 1 second into millisecond. Okay, then in that case, there is unlikely that 2 guys comes in at the same time. So each interval, only 1 guy may come in or not, and the p is very small. Okay, because you cut the interval is so small, then only 1 guy will comes in, right? So with this interpretation, it just can interpret number of success in the binomial is just how many people would come in this period, right? So we just take the binomial, okay, to interpret in the way that how many number of events will happen in a certain period of time. Okay, so say how many customer will come in a time interval. Okay, how likely an accident will happen within a certain period of time. Okay, so there are a lot of applications on those because you often model how many people come in, right? It's a dynamic process. Okay, do note that when you model the time horizon number of events in this way, some property from binomial will transfer to this one, right? Because one thing about the binomial is the outcome of the first box, right, is similar to the second one, right? And so on and so forth. Each one is independent. Okay, when you put it to the here, Okay, you must also accept the same assumption. We're saying that if there are many people come in the first minute, okay, wouldn't affect the subsequent, right? And that is true in many cases, right? Consider a restaurant, right? And people come in, right, in the first 15 minutes, so doesn't affect the rest, right? But there are cases and whole. Imagine you are in a small cafe with a glass door where people can see how congested it is, right? If there is full now or many people comes in, then probably there are two occasions. One, they may wait or they not, right? If they're willing to wait, then actually more people comes in, actually more people will come in the subsequent time, right? Or people are busy, right? So people probably would not come in when they see no seat in the restaurant, right? So it can go either way, right? But if you think that is not an important concern for your modeling, which like accident, right? Something would happen, whether some car accident in Hong Kong, in Arrogate, right? Something happened in the morning doesn't affect something happen in the afternoon, right? Unless talk about, say, typhoon comes in and big wind comes in, then they may be correlated, right? But in general, this is a good assumption, okay? And of course, in application, consider the case of customer arriving in a restaurant, right? You would think the peak hour, the non-peak hour are different, right? In that case, you will separate the modeling, right? Peak hour, you use one kind of P, right? More people, higher P, right? And when you have a non-peak hour, the P is smaller. So that is not a very big concern with application, because you will see the peak season, non-peak season, right? Same as typhoon, the peak season, non-peak season, right? So earthquake or volcano would be there as a volcano is an active volcano and a not so active volcano. So it's not a big concern, okay? So I hope I convinced you that the binomial actually is very useful, and then we talk about the detail of what we call Poisson very soon after break, okay? In the meantime, I have go around to see if any question. Okay, let's a break of say 10 minutes. We'll resume at 12:30. Just walk around to see if any question. So let's resume. So we have just to remind you what's going on here again, right? I hope everyone knows binomial, right? Just like you have an n binomial trial, right? Binomial trial means you have one trial is a box, right? The box can only draw two outcomes, either your success or failure, right? Success P, right? And failure is 1 minus P, right? And you repeat this n time, but each you just draw this box n times, right? Once you draw it back, right? So that's why each outcome is same. Okay. The question of Poisson is trying to make you have a lot of box, lots of box, and the probability that you drawing a successful ball is very low probability. Okay, and you will ask, what does it bring us? What it brings us is what we call the Poisson, and Poisson is useful to model the case what we call number of events happen in a period of time. Okay, because you can imagine that a period of time, whatever you like, 1 hour, 1 minute, 1 second, you can cut this time interval into very, very small subintervals. Okay, and this small interval, the probability that an event would happen, we call success, right? Or event happen, is very small. Okay, and in that case, you can try to say binomial is how many success, right? That means that how many events are going to happen in this time period, right? So it is useful to model number of events happen over a period of time, number of, say, customer arriving here, number of earthquake in a period of time, number of typhoon, right? These things are very much useful because, right, that's how you model a lot of things, right? Because time dimension is important, right? Because this is how you're trying to usually apply binomial in practice, right? Just how many people apply coming in today, right, or tomorrow, or this tonight for a restaurant, right? So and so forth. Okay. So this like what I said, partition the time period n small interval. Each time interval has a binomial trial, and each trial has a success probability p, and each trial independent. Oh, sorry, the typo t should be TIAL trial. Each trial is independent, and x number of success. Okay. And do note that here we have the support of x is n is very large. Okay. So that's why we can go to any n will be very large, so up to n, but n will be infinity. Okay. So in that case, if you some mathematical step will tell you if you this, when n is very large, p is very small, it turns out like look like this way. Okay. So turn out to be, it doesn't really matter what is the value of n and p separately. Only it matters just n and p times together. Okay. But what's NP? NP is the mean of the binomial, right? It doesn't really matter what is the n and the p, but rather the lambda, right? It doesn't really matter how you divide the interval, right? And only the p would be a concern, right? Because within time interval, right? It doesn't really matter how you cut it, right? Because you cut it smaller, the p will be smaller, right? If you cut it into a bigger n, you have smaller p, right? If you have a bigger n, you have smaller p. You have a small n, a bigger p, right? If you consider the process, right? So that's why only matters n times p. Okay, in that case, so which is the mean, and here we will use lambda, okay, instead of np because we don't need to really keep track of the both. So that's why the preference is like this. Okay, this is just nothing but coming from this guy, right? Just replace np by lambda. Okay. So here the only interesting thing is e. What is e? Is the natural number, 2.718, and I guess this is if you learn math M1, then you know what is this number. And if you don't know, then it just e. I think if you just you can just check out the internet and see what's going on there. But e is a number that often comes out when you look at advanced math. Okay, but for your purpose, it's just a number for you. Okay. And in this particular case, you expect to see mean is same as lambda. It's not surprising because it's binomial, right? Binomial is NP, right? Binomial, remember, binomial is just NP, right? So NP is lambda. There is nothing surprise you at the mean. Okay. What is surprising is this variance, right? Because variance would be NP times 1 minus P, right? So why we have lambda as well? The reason, I mean, I'm not going to prove it, but the intuitive meaning is this is lambda, right? There's no problem. But this is close to 1, right? Because we say P is very, very small. Okay. So that's why you can ignore it. That's why we have lambda. Okay. That's the idea. Okay. Of course, the real proof will actually require proof. Okay. It's not saying that this is the explanation, but this is the intuitive way to see why it is a right one. Okay, but to understand fully, you actually need to go to proof. Okay, but binomial have the feature that the mean and the variance are the same. Okay, so some may say this is a good thing, but some may say this is drawback from this, but it's what it is. So that's the thing. Okay, so just now you know they're the same mean and variance, and that is very special property. So that's why when you try to look at the data, when you see the mean and variance are equal, that gives you an idea that it's probably Poisson. Okay, when experts talk about number of events happen. Okay, so that is the thing. And okay, so let's see the example and try to convince you that it's very useful one by looking at the following example. And before we do that, let's see the graph. And just to remind you that why we care about the graph is looking at the graph is because usually we look at the data, and from data we infer what's the lambda, okay, and what the distribution looks like. Then if the data looks like this, then probably it's good to say Poisson. And this graph also remind you that when lambda is small, the graph looks like this, right? And when you have a bigger lambda, it really looks like a bell curve, right? And then actually this is true when lambda is large enough, then there's no problem to use a bell curve as you learn later. Okay, so but that is something we don't cover in this class. But bell curve is basically very useful when a lot of things would happen. Okay, and let's give you an example why Poisson is very useful. Okay, so this is the problem. Okay, we have a restaurant. Okay, and each hour people comes in, following Poisson distribution with mean 5. Okay, the question first is why you assume there's a Poisson. Okay, and I guess why we convince you that try to model how many people come in given the hour, given time periods, we know only Poisson. That is the easiest thing to do. And how you come with number 5? Look at the data. Okay, on average. Okay, how many people comes in? Then its average is 5. Then you can safely assume that it's 5 mean 5, right? Because this lambda is, that means that this is, when we say mean is 5, actually we say lambda is 5, right? Okay. And how you get it? You just look at data. Each hour, how many people comes in? On average is 5. That is, then you put 5 there. Okay. That is coming from historical data, right? Look at the data. You figure out the mean is 5. Okay. When you try to predict the future, you also use 5 as the mean. Do you see how we apply in the practice? Okay. The 5 not coming from the sky. Okay. The 5 come from data. The data tells you from historically this is 5. That's the 5. And use data, you form your model, which you say, okay, let's say the Poisson would fit this well. And using the Poisson, we can under this assumption of Poisson, and then from data 5, we can predict the future, which is the following. What's probably exactly 2 customers comes in the next hour. Okay, exactly 2. Of course, maybe more than that, less than that, but this is just lambda is 5, x equals 2, right? So e to the negative lambda x factorial, right? So that is the case. Okay. So exactly 2 will be very unlikely, right? Because the mean is 5. Okay. So we expect actually should be around 5, right? Maybe 5 or 6 or 7 would be more likely because binomial, right? So expect too much because mean is 5, right? Should not be too deviate from 5, but that actually the data actually tells you, okay, is 2 is very unlikely, right? So actually, basically, you can look at the graph before, right? But not exactly 4, but this is 4. Then you can see mostly concentrated around the mean, right? It's a bell, more or less a bell curve, bell shape, right? So just like to be around 5, okay. So I get this give you idea how you can apply in your practice, right? So you can see how many people comes in coming hour, right? and then you can make business decision. Okay, I hope this is helpful. Okay, and if you want more application, you can check out later the assignment or look at everywhere internet. Look at Poisson, you will Google it, you will see huge number of search results tell you how to use Poisson. Okay, but now I think that you will not be worried about the Poisson. I mean, especially when you first time learn it, you will be scared by factorial and exponential and the E and all the things, right? But I try to convince you that there's nothing different from the binomial, the combination, right? Which is something you know very well. Okay, but just a shortcut when n is big. Okay, this is how it comes about. Okay, and it actually comes from why we have Poisson is actually coming from the idea when we do before the computer, right? Calculating this combination is very time consuming, but calculating this is much easier. Okay, actually this, I mean, why the Poisson comes out, right? One of the reasons, but actually you find it's a very useful application. Okay, is there any question? Any question? If no, then I would talk about our very last one. We call hypergeometric. Okay, hypergeometric. So hypergeometric, as I will say very soon, that is you can easily contrast it, compare with binomial. Okay. So let us, before we go to the notation, let's consider this again, binomial. Okay, I use the same color here. Okay. Oh, sorry, I should use the same color. Right? So binomial, we have 1, 2, n, right? And we have either success or failure for each box, right? Success or failure. And we say S is 1 minus P. Oh, sorry. Success is P. And failure is 1 minus P. Right? So, and this is same for every single box. Right? So you try, right? And thinking in your mind, right? Just what is it is just the following, right? You have a box, okay? Say a box of 100 balls, okay? Then we will have 100 times P number of balls that has a successful there, right? And there will be 100 times 1 minus P of ball that have failure, right? So a bunch of S, the bunch of F, right? So on and so forth, right? So you can imagine that every time from this 100 ball in the box, you just draw one ball there, right? And once you draw, what's the result? You go to the first box, right? And then go to the second one, okay? You do the same draw again, okay? But each time after you draw the ball, you put it back, right? So this is a ball draw exercise. You do it n times, right? Okay, and sometimes we call this, we do a sampling with replacement, right? We just look at the thing and put it back, okay? So this would fit many scenarios, right? If they're independent, right? But some other time that you do not put it back, right? Say, for example, that is what you do when you do audit, when you do quality control, okay? Say I put the case audit. You go to a warehouse, okay? And you are trying to say there may be 10 or 100, maybe 100 of say inventory or machine, okay? And you are trying to draw one of it, okay? And see whether you are doing inventory check, okay? The box there, the 100 box, okay? And there may be some number of them are empty, some of them not, okay? Okay, then you have to take one out and see whether they're empty or not, right? Or there's a good there, right? Suppose the firm claim that 100 box of inventory with maybe iPhones, I suppose, or smartphone, right? And You don't really know whether there's iPhone there, right? Or just another regular Xiaomi phone, we don't know, right? And then you try to check out, right? Open a box and see whether there's iPhone there, or just a Xiaomi box, Xiaomi phone, right? And then once you open, you don't put it back, right? So you just check box, maybe 100 box, you only check 30 box, okay? And then you want to see how many actually are the iPhone they claim, okay? Then in that case, you just put one box and then so on and so forth, right? So that means that each box you open is a little bit different, right? In that case, suppose you have first draw, you're going to draw, it will be, say suppose in this case, right? What I claim is now I have a 100, the 100 box of stuff here, right? And suppose I would say maybe 80 of them are real iPhone, okay? And 20 of them are, I don't know, Mi phone, I don't know, whatever you like, okay? Or maybe this, maybe this easier, J phone, okay? iPhone worth money, J phone is a nothing, okay? And it's a fake phone, okay? And what you're going to do, maybe you pick 10, you do audit, right? You don't do everything, right? You just basically maybe you just do 10 sample, okay? The question is, okay, you just draw the first draw, okay? How likely you're going to have an iPhone, right? It's going to be very simple, just 80 over 100. That's not an issue, right? Because that is what it is, right? But the second one is a little bit complicated. It's no longer 80 over 100. It really depends on what is the first draw you have drawn, right? If the first one is a J phone, okay, then you become 80 over 99, right? Because you draw one already, right? You draw one iPhone. If there's iPhone, it's 80 over 99, right? If the first one is J phone. But if the first one is iPhone, then you become 79 over 99, okay? So each time is very different probability, right? Depends really on the first draw is iPhone or not, so on and so forth. So each draw is dependent, okay? The question, of course, is what is the number of iPhone you drawn out of sample of 10, okay? Let me rephrase the question again. What's going on is we have a sample of 100 box of phone. I don't know what it is. Either they are iPhone or they're J phones, okay? And you try to draw 10 sample of it, okay? And we are asking the random variable is out of 10 sample, how many actually are iPhones, okay? Can be one iPhone, can be two, can be up to 10, right? From 0 to 10, okay? And the difference between this and the binomial is once you draw the phone, you put it back, right? But when you do audit, sample check, quality control, you don't put it back, right? Just take it out and that's it, okay? So what happened for the second box depends on the first box, right? If the first box is J phone, right? If your first one is iPhone, it becomes this one. This is the probability that you have the iPhone a second one, right? So each one is dependent, okay? So the question is, how can you calculate this probability? Okay. And for all the application, how do you make the decision is, right? Maybe you further figure out that the probability of having, say, this is what the people claim, right? This is the firm claim that, I mean, this is the case, or you believe this is the case, right? But you don't know which one is going to be this is it, right? But if you figure out that there are many J phones, right? Then you just query whether the claim is correct, right? They say 80 is good, 80 is an expensive phone, 20 is an inexpensive phones, right? So if you have, say, 8 or 9 or 10, probably you would not be very happy with the audit, right? So then if you're 9 or 10, then you were very happy, right? But you have 1 or 2 or 3 or 0, right? You have 0 probability that you will think that guy is cheating, right? But you have what about your 4, 5, 6? Okay. Do you think this is a reasonable outcome, or do you need more sample that depend on probability you having those numbers? Okay. So let's see the case again. I mean, so here we have big N of number of items. In the case of iPhone, J phone is 100. Okay. And number of good items is called iPhone, right? We have 80 iPhones. Okay. Out of 100, right? So we have 100 there, or N, right? With A, that's good, right? The 80 of them, right? And 20 of them are N minus A are the bad phones. They're called J phones. Okay. And out of this, I'm going to draw 20 of them, okay, which is, sorry, I do 10 of them, right? 10 of them, that's called a small n, okay? Take n item, okay? And we're asking the random variable is how many good item, okay, so draw them, how many of them are iPhones? So there are 1 up to n, they are iPhones, okay? And do note that this n must be less than a, okay? Because otherwise otherwise the rest must be the bad phone, right? Because if you draw enough number, there must be a bad phone. So now I try to convince you that this probability is just this guy, okay? Looks crazily complicated, okay? But I'm trying to convince you this is not complicated, okay? So let's see the following, okay? First, look at the denominator, okay? We have 100 of phones, right? Each can number from 1 to 100, all right? And how many ways you can draw it? It's just NC, big NCN, right? Right, just this one, right? Because the n items, you draw n of them, how many ways you draw it is NCN, right? And how many ways you can do these two is what? Let's see what's going on in the first one. Let me use another color, orange, right? This one is what? This one is out of a number of iPhone, how many iPhone you have to draw, right? This is the good outcome. Okay. And the green one, this is all the bad, right? Because n minus a bad item, you actually draw n minus x out of them. Okay. And why you multiply? Because this is just what we call the principle of counting, right? Just you do two things, just multiply. Is that clear? Okay. I hope I convince you this is right. Okay. Is that okay? If you would not really convince, you can just convince yourself the following. So in the case of iPhone, 100 iPhone, okay, what you're going to do is the following to convince yourself this is right. Okay, you have the following. You have 1, 2, up to 80. They are good phones, right? Or iPhones, or good thing. Okay, the good thing, good item. Okay, and from 81 up to 100, they're bad, right? So you're going to, how many ways you can draw it, right? Draw this thing, right? There is just 100 C10 because you want to draw 10 ball out of it, right? You don't care about good or bad, you just draw 10 out of it, right? And how many ways you can draw good phone, right? Just like how many ways you can take out this, how many back you can take out, right? Suppose it's, then you get 80 times x, right? And there will be, then that would be the other one will be 20 times 10 minus x, right? Suppose you draw 10 balls over there, you just try to fill up to 10, 1 up to 10. Okay. Is that clear what's going on there? Okay. So, I mean, of course, I mean, you may not fully appreciate the formula, but I hope I convince you this is the right one. Okay. And if you still don't fully convinced, then you just take it as assumption. Okay. You think it's right, and after a while you will believe this is true. Okay. So in this particular one, the mean will be just n times over n. Okay. So this is somewhat a little bit surprising, as you will imagine, because a over n, okay, is indeed same as p. Okay. If you repeat this, okay, like binomial, you're supposed to put it back, right? You put the outcome out and you put it back, right? Each time should be a over n, right? You draw it with replacement, that is a over n, right? So it said hypergeometric is very funny thing is the mean is actually no difference, same as NP. Okay. So it sometimes actually does mean that when you do sample with replacement and without replacement, the mean is the same. Okay, that is actually the fact. I mean, coming from here. Okay, sample without replacement and sample replacement, actually the number of item has no difference. Okay, just mean if you don't convince, you can convince yourself. Look and following. You have a ball of box. There's a red ball and black ball. Okay, calculate the number of red ball. Suppose you draw 10 times, or right, and then you look at the outcome that sample replacement and sample replacement. The number of ball you actually draw, okay, on expectation, the same thing. Okay, you can convince by doing experiment by yourself. I mean, whether putting ball back or not have no impact on the mean. Okay, but it doesn't mean everything the same. Of course, you will see. Look at the variance. This is NP. Okay. And this is the middle one is what is 1 minus p, okay? Because n over n is 1, a over n is p, right? So you will see this is exactly what you would expect to see when you have binomial, right? Because np times 1p is binomial, okay? So what is new here is this guy. This particular orange guy. This orange guy, as you can see, the math is less than 1. Right? So you will see when you sampling without replacement, the variance is smaller. Right? Because you multiply something less than 1. Right? And let's think about why this is true. First, we understand why the variance is smaller. The reason is being that once you keep drawing, okay, no matter how you draw at the end, the pool shrinks. Okay, that means that the variation is getting smaller, right? Because imagine that if you draw everything from the box, there's no variation, because suppose that you are going to the n is going to very close to big N. Okay, that means that you're almost drawing almost everything from there. Okay, so at the end of the day, there's no variation because you're drawing almost everything from there. That's, I mean, basically draw everything, then it's just no difference, right? And you look at the case, right? And if you look at the case, n is 1, right? When n is 1, okay, that is exactly the same thing, because when you draw once, there's no sample with replacement or without replacement, right? So the two things, n is 1, get the same thing, right? And when n is very large, okay, it's very large, very, very large, okay, this will become very small, right? Because there's no variation, because you draw almost everything there, right? Just like the big box, you keep drawing, right? At the end, then you almost know what's going on there, right? No matter, it doesn't really matter how you draw, right? The way that at the end the same. Okay. So that's why when you drawing things without replacement, the variation get shrinks. Is that clear what's going on? Is that okay? I mean, just interpretation, I don't think we need to worry about this, but just to give you an idea what's going on. Is that okay? I mean, not super important, but I hope that will be clear. And as you would expect, this graph, small n like this looks like a very bell curve, bell-shaped style. And indeed, this thing actually true when you have a big N, big A, then you will see kind of a bell curve style. Okay? When everything goes big, then bell curve will apply. Okay, but when you don't have, say, you go to audit your auditor, then probably these things you will concern you will make you a big concern. Okay, so of course, in our class we don't go further from this for geometric. Okay, but when you try to learn quality control audit, then hypergeometric will be commonly used. Okay, we just learn it up to here, and that's for the hypergeometric. Except maybe we give an example. Okay, let's say a warehouse. Okay, and there are 30 computers, 4 of them are defective. Okay, the question is being that what's the probability 2 of them are defective out of sample of 6? Okay, I mean it's very unlikely because you say 30 computers, only 4 are defective. Okay, but the question is, okay, this probability 2 out of them are defective out of 6. Then this comes out, I mean, without going into detail first, and the probability is 15%. Okay, so you would think that by chance that's very unlikely. Okay, so if the guy, the audit or credit control, you say 4 are defective, they claim, and you try to do this, then you would try to think twice whether the firm is doing the claiming the correct, right? I mean, the 50% is very unlikely that however it comes out, right? And 50% is non-trivial, so you would probably want to take out more sample to see whether this is a problematic thing. Okay, so now we go to see how to get this number, right? And it's 30 because there's total number of them, and you will say defective is what we call the success. Okay, because we only care that is what we're asking, the probability of them are defective. Okay, although it's defective, but it's success in our case here. Okay, so success or failure is different from defective. It's just like whether what we count. Okay, but here the defective successful item. Okay, we draw 2 out of it, right? So that's why out of 6, right? So that means that we have a small n is 6, right? X is actually 2. Okay, because we draw 6 out of it, and we want to calculate 2 of them are defective. Okay, so that is the problem, and you can easily see this is have a lot of application because this a lot of time actually doing sample without replacement. Okay, especially when you do the sampling that have to be destroyed. Okay, say suppose you are looking at the food, right? And to see whether defective or not, you actually have to open the thing, right? And put the chemical there and see whether they're okay or not. Or the wine, whether they're defective or not, you have to actually open it and try to string it. But once you open it, you cannot put it back, right? Because the wine, the thing open is not. So that is sample replacement is often because you have to destroy the sample, right? So that is something that unfortunate, but that is happen a lot of time. Okay, I hope that convinces you what's going on there. I mean, if you sample the thing, you don't have to destroy it, right? Then you can use binomial, right? And you can see here from the mean and variance calculation, and you can see when big N is very big, small n is very small, okay? And you should expect binomial is a good approximation, okay? So what I meant is, if here we have 300 computers instead of 30, if you do this by using a binomial, actually it's no different. Very small difference. Actually, you can try it yourself at home and say, suppose you have 3,000 computers, okay, so on and so forth. Actually, there's no difference. So when you have very big, the big N is very big, okay, that you calculate binomial has no difference, okay. But in many cases, you don't have such a big N, right? So that's why hypergeometric comes in handy. Okay, I notice many of you are doing the accounting, so that would be, I think, the most takeaway from this one, right? Any question? If no, then we will just quickly talk about continuous random variable. I mean, I don't go to deep detail because we don't have enough time, but just give you the idea what we'll be doing. It's called random variable. Is we will have, at the beginning we said, for the continuous random variable, we only can define what's the big F. Okay, we don't have the big P again. We have only big F. Okay, the big F is the same idea. For the P of X is less than that value. Okay, we no longer have the P. Remember what's the P? P is the probability that P of X is probability that a big X equal to this value X, right? And we don't have this anymore because continuous random variable, you have any value, a lot of value possible, right? And in that case, right, this is not feasible because there are many number of value, right? So a particular value equal to that number, okay? In our case, it's always 0, okay? In continuous random variable, in general, that will be 0. Why? Look at the Hansen index, right? So Hansen index may be now like 30,000 to say 20,000, right? And today the value at a particular number goes to 0 because it can be any number, right? It can be any decimal numbers, right? So I put up a number there, then end up in that number is very unlikely, right? So that's why it becomes a 0, okay? And you will see when you have continuous random variable, okay, we end up with something like all this notation that looks terrible if you haven't learned calculus, okay? And I try to convince you that this is just same as what we said, right? The summation of y less than x, okay? P of y, okay? This is the same thing, okay? Because you can, if you don't know calculus, this is what we call the integral. Integration side is just the summation. It's just a summation, the summing. But when you have many continuous, you have small part, then you have to do the summation. It's the same thing. So basically, we replace the integration side by summation. That's exactly the same thing. Okay. And you can see the difference is here we have the F and the P here. Actually, the F and the P play the same role. We don't have F anymore, but we call it something called F. And F is called sometimes we call the density. Okay. Or they don't call distribution, but they call density. It depends on which book you are using. Some book they call that probability density function or probability distribution function. Okay. And if you learn physics in the high school, then you know what density is, right? The mass of the object and density of the object, right? You integrate the density, you get the mass, right? So that is how this name comes from. But here is why you have this thing here. Okay, if you learn calculus or math, advanced math, then you will know the integration and the differentiation are just reverse operation, right? Just this addition, right? This is subtraction, right? Or this is division, or maybe, or this multiplication, this is a subtract division, right? Or the inverse operation. That's what we call why this is the case is what we call the fundamental theorem of calculus. Okay, integration or differentiation are the opposite thing. Okay, but since we are not the math class, so you can just safely forget about this. Okay, And that's the definition of the differentiation, right? Basically just a slope, right? But I don't think we want to go further more than that. The only thing you need to remember, indeed, is this guy only, which followed directly coming from the discrete case, right? That's the only thing you remember. The big F, right, is just the probability that the random variable less than or equal to that value, okay? The only thing probably you would concern you a little bit is slightly different, is because of equal to particular value 0. So this in continuous is same as this guy. Okay. Whether you're equal to or not has no difference in continuous, because the random variable equal to particular value is 0. Okay. So that is the only thing probably you would be remind yourself when you continuous, that's same as discrete when you talk about cumulative, and everything goes smoothly. Okay. And you don't need to worry about integration. Okay. The reason is being that we will use calculator Excel, okay, to do all the calculation we need, all of the tables. Okay. So that's why you are not doing the calculation. We will just give you you will just use calculator to calculate the things that we need, okay, in particular case here. Okay. And in general, when you have cumulative probability function for continuous random variable and calculate this, is in math there's no closed form solution. So basically rely on computer to do it anyway. Okay. So even people actually in practice don't actually do the calculation by hand unless you are doing something with special case. Always you do computer. Okay, just like the engineering, the physics calculation. Okay. So so at the very last minute, I want to say, I mean, these four are the same thing. Okay. For when we have continuous random variable here. Okay. And the reason is being that whether equal or not, they're the same. Okay. And this guy, right, you can rewrite it as x less than b minus x less than a. Okay. So that's how you get this formula, right? Because it's a math problem, right? If you look at the graph here, right, you have b here, you have a here, right? The question asking the red area, okay? And from the kindergarten, okay, you know the red area is the blue area, okay, minus the green area, okay? Blue minus green is red, okay? So this is blue, okay? This is blue minus green is red. Is that clear? Okay. This one we will be using it for the class. Okay. Basically, this is the main thing you need to remember for the continuous random variable. And of course, we will learn different things in the next week. So that's the end for today. Just remember your homework too. I think it's due next Friday. Right? So I'll see you next week. Thank you. Have a nice day.